Now, this first question states that there is a thing called C4 H8O, and it can represent a number of compounds which have different functional groups and which show different types of isomerism. Compounds H, J, and K each have the molecular formula C4H8O. In each of the molecules, he's told us a few things. He's told us that the molecules are not cyclic, which means they're unbranched as well, which means that they are basically the carbon chain is unbranched. So all four carbon atoms are basically in a straight line. Okay, it's unbranched and it's not cyclic. Cyclic means, as the other one is no oxygen atom is attached to any carbon atom which is involved in pi bonding. So, so the oxygen atom has nothing to do with a carbon atom that is involved in pi bonding. That's making a double bond, basically. Pi bonding comes in when an atom is making double bonds. Uh, then he says that compound H reacts with sodium metal and a colorless flammable gas is produced. So there could be two things. So one thing that we can rule out is one thing that we could rule out is, and let me also check whether we did this. I mean, some of the missing reactions, because I think while we're doing alcohols, I mean, we did carboxylic acids. I do remember missing out on one particular reaction for alcohols, and we talked about esters. We talked about uh, no, we did talk about alcohols being weak acids. I hope this is the same board. I think. I said we did talk about alcohols being weak acids, and I told you the reason why they were very weak acids. That alcohols have an OH, and the H over here could break off, but it usually doesn't break off because the oxygen, the negative charge on the oxygen is very large. Because the carbon chain over here has an electron donating effect that increases the negative charge density over here. And when it increases the negative charge density, the H plus one is attracted very, very strongly, which is why they don't really, the H plus one doesn't leave or it doesn't ionize that much. And alcohols have weaker ionization even compared to water. Now, water ionizes very badly, it produces very few ions, but alcohols are uh, even weaker compared to water molecules. And anyways, the point is, alcohols behave as acids, but they only behave as acids, but with highly reactive. I mean, it's usually don't behave as acids, but only behave as acids with highly reactive group one metals. So the sodium comes in, knocks out the H, and H2 gas is produced as a result. So that's what's happening. So now, if you go back to the question, you would notice that the molecule over here has just one oxygen. Now, now if it has only one oxygen, it could be a number of things, but it can't be a carboxylic acid. So it's not. I mean, you know that the functional group cannot be carboxylic acid because for carboxylic acid, you need two oxygens. So that's not a possibility. So what is possible? It's either an alcohol or it could be an aldehyde or a ketone. Like it might have C double bond O in it. I mean, that's the other possibility that, I mean, two things. I said, but this one is definitely an alcohol. H is an alcohol, right? Because it's reacting with sodium metal. Is this part clear to everyone? Ethan, is this clear? Isaac, clear?
Yes.
Acha, so, and nothing else is given about H. And yes, I mean, there's other information about J and K. Uh, and he's saying that there are three possible structural formula of H, right? So I know that H is an alcohol, C4H8 and O. So how many different types of alcohols could I have? I could have an OH here. That's one. The carbon chain has,
सर
yes.
सर इसने स्ट्रक्चरल बोला है तो हम CH3 CH2 करके नहीं लिखेंगे?
अच्छा वो नहीं, पहले तो उसने सजेस्ट पॉसिबल स्ट्रक्चरल फार्मूला, ठीक है, मैं एक्सप्लेन कर दूं स्ट्रक्चरल फार्मूला, ठीक है. Whenever structural formula is mentioned, na, structural formula is any formula that shows structure. ठीक है, मतलब all of these structural formulas has different versions. This is known as a displayed formula. A displayed formula is a type of structural formula. Okay, जिसके अंदर you show all the bonds, even the OH bond. ठीक है, so structural formula, remember, is a general term. Any formula that shows the structure of a molecule, that's a structural formula. You could have shown the skeletal formula: 1, 2, 3, and 4 carbon atoms, and on the fourth there's an OH. That is also a structural formula. या फिर वो condensed version would have been CH3, CH2, CH2, another CH2, and OH. ठीक है, Isa, is this
डिपेंड्स
clear?
आपने क्या, आपने क्या लिखना है, आपकी मर्जी होती
Isa, is this clear?
है. यस.
अच्छा, mic off कर. So that's Ethan, is this clear? Mohammed, is this clear? Structural formula. Okay, any formula that shows structure, that's a structural formula. And structural formulas have three versions. One is the fully displayed formula. You could write a condensed formula. You could use a skeletal formula. All would be acceptable. The reason a lot of times in the marking scheme this formula is written is because you don't have space. Like if there's a one line answer, you write this. But over here, you're given space. So you can draw the whole thing. I say anyway, so I'm going to draw the whole thing. So now coming back to this. This is the first one. Keep the OH together. So that's the first one. Um, the second one, another alcohol. Another alcohol would be all four carbon atoms have to be in a straight line. I mean, that was the condition that was mentioned earlier. So all four carbon atoms, they have to be in a straight line at all cost. So the other one could be that the OH is on the second carbon atom. And there are three hydrogens here, two hydrogens over here, and three hydrogens over here. And there would be an H over here as well. As I tell me, what could be what could be a third version of an alcohol having the molecular formula C4HNO? Any idea?
So functional group change भी हो सकता.
Yeah, will there be like an ethyl group?
Will they be in?
Ethyl group.
See, over here they had specifically stated that the carbon chain is unbranched, and the carbon chains are going to be in a straight line. So you can't branch this, right? I mean, you have to follow the instruction. The carbon chain is unbranched. Ethan, is this clear?
Yep.
Okay, now they're saying suggest possible structural formula for HJ. Now the only possibility is, I mean, these are the only two possibilities. Like the OH could be at the fourth carbon atom, or it could be on the carbon atom on the second one. Because if you attach an OH over here, it's going to be the same thing. So the only possibility is, because they hadn't talked about, I mean, they weren't mentioning structural isomers. They just said isomers. What they just said that there three structural formulas are possible for H. I mean, they are talking about structural formulas, but only one for J and K. The only possibility is that this one is chiral. So that's probably the only possibility. And I thought we got one thing wrong. Did we get this wrong? I thought we got one thing very wrong, which was it was C4H8NO, not H10. Now I've drawn H10. Now for it to be H8, there has to be a double bond somewhere. So let's add a double bond. Okay, we had missed out on a double bond because the number of hydrogen atoms were 8, not 10. So let's have C4H8NO. The same is true for this one as well. Like the OH could be Okay, so the OH could be on the, I mean, there could be a double bond here. And this is, so these are your, that's your OH, and this is your OH over here. So that's two. And they had also explicitly stated that the oxygen atom should be kept as far away from the pi bond as possible. It should not be attached to any carbon atom which is involved in pi bonding or which is forming a double bond. So the third possible structure could be that the double bond is in the middle and the OH is at the end. So that could possibly be a third one. Okay, so in the first two, I mean, apart from these three, nothing else is possible, as long as you want to meet the conditions that the four carbon atoms should be in a straight line. Uh, the OH and the double bond should be as far away. I mean, they shouldn't be on the same carbon atom. So I have to keep the OH away from the double bond. Okay, Isaiah, is this clear? Ethan, Mohammed, is this clear?
Sir,
Yes.
Yes.
doesn't that make the last one an optical isomer?
No, it's going to form. I mean, you're saying that the last one can form optical isomers, right?
Yeah,
No, it can't. It's not going to form optical. This one, right?
yeah.
I mean, this one would form geometric isomers, not optical.
Oh, wrong.
I mean, it's going to form geometric isomers, not optical. I mean, this one is going to form optical isomers. The reason it's going to form optical isomers is that there is a chiral carbon atom. Like there's a carbon atom that's bonded to four different groups. So this one is the optical isomer. This is the one you get geometric or cis trans isomers around the double bond over here. I mean, it's definitely going to ask about that. The reason we did not draw any stereoisomers over here was because he was specifically talking about structural formulas, which means that the structure had to be different.
Right, so it doesn't matter if you draw like a cis or a trans, you'll still get the mark.
Yeah, right now, because he's only asking for the structural formula.
Okay.
I mean, remember, the structural formula only gives you the connectivity, which atom is connected to which. I mean, when you talk about stereoisomers, then you have to draw the three-dimensional shape of the molecule. Like the molecule would not actually look like this. I'm going to do it here. Like this molecule is going to exist in two forms, right? Around the double bond. Because the actual shape around a double bond is trigonal planar. So, and the angles would be 120. So this carbon atom over here has an H and a CH3 bonded to it. So there's an H and there's a CH3 group bonded to it. This carbon atom, on the right, has an H and a CH2OH bonded to it. And the other one would be, I mean, it's going to be H. This side would be switched, that the H would be pointing downwards and the CH2OH would be pointing upwards. But to show this, you would have to draw the three-dimensional formula. So when he's talking about the structural formula, you never you can never show the stereoisomerism in a structural formula because structural formulas don't deal in shapes. So as long as you're drawing the structural formula, both of these they would look like this in the structural formula. Or if you write the condensed version, they would look like this, like CH3, CH double bond CH and CH2OH. Now, by just looking at the structural formula, you wouldn't know whether you're talking about this molecule or this molecule. Mohammed, is this clear?
Yeah.
Achha, so, Isaiah, is this clear? Ethan?
Yeah.
Achha, so three alcohols based on the conditions that he had mentioned. Now let's focus on J and K. Now J and K give an orange precipitate when reacted with 2,4-DNPH. Remember, 2,4-DNPH is a test for aldehyde and ketones. So that means one of them is an aldehyde, the other one is a ketone. Carbonyl compounds. Let's open the Where's aldehyde and ketone stuff? Probably this one. Nee, I think we did it after this. So hydrolysis carbonyl compounds, yes. So identification, this was 2,4-D pH. That carbonyl compound identification, aldehyde and ketones, carbonyl compounds are both. So you have 2,4-D pH and it's reacting and it's this is the 2,4-dinitrophenyl hydrogen. You get an orange precipitate when this reaction happens. Okay, this is orange precipitate. That's the observation. And then how do you differentiate between an aldehyde and a ketone? This we studied in alcohols, oxidation of alcohols. The way you differentiate oxidation of alcohols, aldehydes they get oxidized by Fehling and Tollens. They get oxidized to carboxylic acids, while ketones don't. Ketones oxidation stops at ketones. They don't undergo any further oxidation. So that was the difference between aldehydes and ketones. So going back to the paper, K reacts with Fehlings. So that means K is an aldehyde. It's getting oxidized. So it's an aldehyde. So C4H8 and O. So the aldehyde would have a double bond O right at the end. And it says C4, that's C4H8. So let's see if we need a double bond. We don't need a double bond. You have your 8 hydrogens. And this J would be a ketone since it's not undergoing oxidation. So it would be C4. The carbon chain has to be unbranched. So to make it a ketone, this would be a double bond. So 3 H's here, 2 H's here, and you have 3 hydrogens on the other one. Is this clear? Aldehyde and ketones. Either is this clear?
Yep.
Yes.
I said, and now he's saying draw the displayed formula. Now when you talk about the displayed formula, you have to show all the bonds, every single bonds, the ones that are showing cis trans isomerism. So we did draw them, but not the displayed. When you talk about the displayed formula, you have to show. I mean, you don't draw CH3, you draw C with all the 3 H's. So just make that change. I mean, CH2OH over there. Don't write CH2OH. It should be C and there would be 2 H's and OH. Here's, this is how you're going to draw it. Fully displayed, which means every single bond should be drawn. Do the same over here and over here. So that was the next part. And then he's saying draw the displayed formula of those isomers which are chiral, and again displayed formula. Indicated in each case the carbon, chiral carbon atom with an asterisk. So which one is chiral? This is chiral, right? So it's this carbon over here, which is tetrahedral. So we're going to draw that. It's going to be carbon. And that's your tetrahedral carbon. It with the, I mean, this one. So you have an OH, a CH3, an H. So you have an OH. Every bond should be shown. A CH3. And I think there was an H over here. And over here there was a double bond with H's. So that's your chiral carbon atom. And then you draw the mirrored version of this molecule. The mirrored version would be uh, everything should be mirrored left to right. So this should be, just a second. So let's keep it this way. So you have a CH3. and you have an H, and everything should be mirrored. It should be carbon, double bond carbon, two H's here, and there should be an H over here. So is this clear? I mean, this should be connected.
Yes, sir.
Yep.
And so this is Kyle, and this was the whole question about isomerism. Now the next one. The next one is many organic compounds, including. So we have to figure out the structural formula of the products that are going to be formed. The first one is what type of alcohol is this? Primary, secondary, or tertiary?
Secondary.
Okay, this one is a secondary alcohol. What's a secondary alcohol? That it's three carbon atoms. The OH is on the middle one, and there would be three hydrogens here, three hydrogens over here, and there's one H over here. So it's this alpha carbon is bonded to two carbon chains. If the OH carbon atom is bonded to two carbon chains, then it's a secondary alcohol. Let's look at the secondary alcohol. What did we study about secondary alcohols? We studied that secondary alcohols, they get oxidized by K2Cr2O7 or KMnO4 into a ketone. Uh, but there is no NaBH4. NaBH4 was a reducing agent. We talked about NaBH4 uh, in terms of reduction. Now, secondary alcohols are formed as a result of reduction. And primary alcohols are also formed when. So, primary and secondary alcohols are formed as a result of reduction. You can't reduce them. You can reduce a ketone and it turns into an alcohol. That's a secondary alcohol. You can reduce a carboxylic acid, which turns into an aldehyde and then turns into an alcohol. So the end result is an alcohol. But over here, as they have stated, there would be no reaction. Secondary alcohols are a product of reduction. I mean, they don't get reduced themselves. Next one is, what is this molecule over here? Like it's three carbons.
Ketone.
Okay, that's a ketone, right? So there's a double bond in the middle, CO, and there's going to be CH3 and three H's over here as well. So that's a ketone. Now toluenes, let's go back and have a look at oxidation. See, ketones don't undergo any oxidation. Uh, this toluenes, I mean, these four things, KMnO4, K2Cr2, 7 toluenes of Felling, they were there to oxidize aldehydes. They don't oxidize ketones. Ketones don't undergo any oxidation. They are the product of oxidation. They don't undergo oxidation themselves. So over here as well, there's not going to be any reaction. Ketones are resistant to oxidation. No reaction. Then you have this one, KOH aqueous and warm, and you have this molecule over here. What do you think this molecule is? Like
Isn't
when do
it
you
ester?
think that's an ester? So we did esters as well, and this ester would be broken down by where are our esters? Okay, so alcohols and carboxylic acids they react to produce ester in water, and the ester can be broken down. Hydrolysis can happen with dilute acid or dilute alkali, which in this case is KOH. So the ester could be broken down back into the alcohol and carboxylic acid. So let's first draw this molecule. It's CH3, then it's CO2, that's C double bond O and O, followed by CH, and then two CH3s, which means that there's a carbon chain, two CH3s, right? This is the molecule. You break it down in the middle. This side would be the carboxylic acid side. So the product would be CH3, C double bond O, and OH. And this other side would be your alcohol side. So it's going to be OH, CH, and then there would be two CH3s attached to the carbon atom. So that's the alcohol side. As I remember, another thing is, I told you when we were doing hydrolysis that during if an alkali is added, you never get the carboxylic acid. You always get a salt of the carboxylic acid because the KOH is going to react with this carboxylic acid to form a salt, a potassium salt. So this is not going to be produced. Instead, this is going to be produced. Is this clear? This is O levels. Shazib, is this clear? Uh, Ethan?
Yep.
Okay, next one. Now again, there's this oxidation happening. What type of alcohol do you think this is?
Primary.
Let's have a look. It's COH, right? And there are three CH3s attached. So tell me what, I mean,
It's secondary.
is it secondary?
Wait, tertiary.
Okay, it's a tertiary alcohol because the carbon over here is bonded to three carbon chains, and tertiary alcohols don't get oxidized. I mean, they're resistant to oxidation. Now, so tertiary alcohols, no oxidation happens. Now, the next one is, let's look at the next one, which is NaBH4. Again, a reducing agent. So that's a reducing agent. And you have a ketone over here. What happens to a ketone? It does undergo reduction, as was done over here somewhere. Where's a ketone? Here's a ketone, right? I should call this a ketone. So this is a ketone. Ketones, they undergo reduction by NaBH4 or LiLH4. And what happens is that the carbon simply changes into an alcohol. It changes into a secondary alcohol. So we're going to do just that. So this simply changes into an alcohol. The double bond goes away, and there's going to be an H added as well. So the ketone over here would turn into an alcohol. Then you have this one. There's an alcohol, and you're reacting it with PCl5. So maybe this reaction, I mean, this was a halogenoalkane reaction. 1 second. So I don't think it's probably not on this one. Where's a halogenoalkane? Maybe there is one. Not over here. Where's the, so that's alcohols. Let's have a look at this.
It's the nucleophilic substitution of alcohols, right?
Yeah. I mean, I'll just tell you over here that when you add PCl5 or concentrated HCl or SOCl2, the OH gets knocked out and Cl takes its place. So it's going to be CH3 thrice and C, and then Cl is going to take its place. That's it. And then you have this strong oxidation happening, acidified, and it's hot as well. What happens? The double bond completely breaks. And I told you that if the double bond breaks, there were three scenarios. I mean, like over here, there's, okay, so there are three scenarios. The double bond is going to completely break. And if the carbon which was attached to the double bond has one carbon chain, what does that carbon atom turn into?
Aldehyde, then carboxylic acid.
Okay, so I mean, so this was the rule that the double bond is going to break. If it has two hydrogens, it changes into carbon dioxide and H2O. If it has on one side there's a carbon chain, that changes into a carboxylic acid. And if on both sides there's a carbon chain, it changes into a ketone. In our case, it's the second one, which is that the aldehyde would turn into a carboxylic. I mean, it would turn into an aldehyde and then a carboxylic acid. It's going to form cetyl bond O and OH. This one would also be cetyl bond O and OH. Plus, this one is a primary alcohol, this other side. And we know that primary alcohols also turn into carboxylic acids. So it would turn into double bond O and OH. So one of the molecules is going to be the H would be gone, and it would be double bond O and OH. So there's going to be ethanoic acid. I mean, draw a neater version of that. It's going to be CH3 double bond O and OH. And there's going to be this molecule, which is this side would be carboxylic acid, and the other side would also be a carboxylic acid. Okay, is this clear?
Yep.
So now the next question probably be related to this. Now he's saying during some of the reactions, the color change occurs. Complete a table for any reaction stating the letter of the reaction and what the color change is. So let's go back. Now talking about color changes. KMNO4 is reacting, so that's purple to colorless. So in G, there's a color change. NaBH4, I mean K2Cr27 is also, is it reacting? No, it's not reacting. I mean, there's no reaction here. And Tollens is also not having any reaction. So the reactions that had color changes were dichromate 6. It was orange to green. But since it's not taking part, it's a tertiary alcohol, it's not going to react, no color change would happen. Tollens, they oxidize aldehydes. So they don't, I mean, this reaction is also not happening. Otherwise, for tollens, you have a black precipitate and a silver mirror forming. So the only option left would be G, which would be turning from purple to colorless. KMNO4 reacting, turning purple to colorless. Okay, that would be the answer to this question. So let's continue with this in the next class then. Okay, I'll try and I'm going to send this worksheet in the group. Just 1 second. So it's a big file. I'm not sure. I sent it in the wrong group. Just 1 second.